Hey there, method students. In this video, we're going to look at how to find the mean and median for a continuous random variable. We kind of just launched straight into it here with a formula and then some practice. So the formula that we use, the mean of a continuous distribution, remember this little symbol here, mu, stands for the mean or the expected value, and that's equal to the integral from negative infinity to infinity, or in practice, it's like the integral everywhere that it's non-zero, of x times f of x with respect to x. So essentially what we do to find the mean for a continuous distribution is integrate over the full interval of the function multiplied by x, right? So we've got this x multiplied by the function. Let's get stuck into it. I think once we do a couple of examples, you'll see that it's a relatively straightforward formula to apply. So in this example, this one's a calculator allowed question. It says for the continuous variable with probability density function given by f of x equals negative 2x plus 10, where x is between 4 and 5, or equals 0 otherwise, we have to find a few different values or things. The first thing we have to find is actually just a probability. This says determine the probability that x is less than or equal to 4.5. So this isn't finding the mean or anything like that yet. This is just saying find this probability. Well, remember that the way we do that is to integrate over the values that kind of represent that probability. So less than 4.5 means that 4.5 would be our upper terminal. And our lower terminal theoretically is negative infinity, but really we just go down to the lowest value before the function stops being defined by this rule, and in this case that's 4. Okay, so we're integrating from 4 to 4.5, the function negative 2x plus 10 with respect to x. That's probably one we could work out without the calculator, but it's a calculator allowed question, so let's do it that way. We're going to plug in the integral, then the function, integrate with respect to x. Pop it in standard mode, and we get 3/4. Okay. Now remember that was a probability, so we had to get a number between 0 and 1. If it was anything else, we would have double checked our inputs, but we get the probability of 3/4. Okay, and just really quickly, not that we have to do it for this question, but as always, it's sometimes good for your understanding to see a graph of what's going on. And so, just going to quickly clear that. Oh, don't be annoying, Kaz. I hate it when calculators don't do what you want. Okay, so what we're really sort of looking at here is just this. I'm going to zoom in on it. This section of the graph between 4 and 5 is kind of where all of our probabilities sort of sit. Okay, you can kind of see just from the grid lines, actually, this is just a triangle with a height of 2 and a base of 1. So you can see that the full area between 4 and 5 would equal 1, which is what we expect. The area that we just found, I'm going to go and actually sketch that. Sorry, analysis G-solve, and then integral with respect to x. And the lower limit was 4, so if you are trying this on your CAS, all you have to do at that point is just push a number and this screen comes up. Upper limit was 4.5. And so that was the area that we just found. And if you're kind of looking carefully and considering that full triangle where the area was 1, well, it makes sense that this area, like this area there, is bigger than that sort of small slither of triangle that's left there. So 0.75 makes sense when we visualize it as well. Anyway, okay, so now when we go to find the mean, okay, well, the mean, this is where we get to practice this new formula. To find the mean of this continuous random variable, well, that will just equal the integral. So just applying this formula. Remember, in this case, negative infinity to infinity is actually just going to be 4 to 5. So we integrate over the full range of x values that the function is not 0. And then inside the integral is x times the function. So x times negative 2x plus 10. Okay. We could write, mu equals or expected value of x equals or whatever. And that's how we find the mean. So what we can actually do here is use a bit of a shortcut. I'm going to copy the previous integral down, change the upper terminal to a 5. I just want to multiply the whole function, and it's important that it's the whole function, so use brackets here. Oops. Using the right way around. Use brackets here and put an x in front. Okay. And that will give us the expected value of x, which is 13 on 3. Okay, so really that's how you apply the formula to find the mean or the expected value. And now as a decimal, right, like 13 on 3 is 4.33. So the expected value of x had to be somewhere between 4 and 5, right, because they're the x values that this was defined for. So the mean still has to kind of make sense. The lowest possible x value is 4, the highest possible x value is 5. And it's, I guess, closer to 4 than 5 because when you consider this graph, it's kind of like more of the distribution is closer to 4 than it is to 5. So it kind of makes sense that the expected value is closer to 4 because that's where the probabilities are a bit higher. Okay, and then this one here, look, I've just kind of thrown this example in because there's one of these in our textbook. I don't remember seeing one of these pop up on exams before, but sometimes when the textbook thinks it's important enough to put it in, I feel like we should just throw it in there just in case. So essentially what we just did in this previous example was find the expected value of x by putting x in front of the function inside the integral. If you want to find the expected value of something else, some other function, like the expected value of 1 over x, you can actually just say, well, the expected value of 1 over x will equal, and you do exactly the same thing with the formula, you just put 1 on x, right, in front of it. Or it would work if that was like e to the power of x, you could put e to the power of x here. So as I said, this is not one you commonly have to use, but just to be safe, in case this ever pops up, well, you've seen an example of how it works. So I'm just going to go back to the CAS again, be a bit lazy here. Rather than type it in all over again, I'm just going to change that x to a 1 over x. I'm going to go back into standard mode first. No, I'm not, because the question said 4 decimal places, and I've just remembered why, because that's not a nice looking answer. So to 4 decimal places, the expected value of 1 over x would be 0.2314. Okay, next one's an exam question. You might actually want to pause the video and have a go at this one yourself if it's a calculator allowed question. And again, it's just practice using the formula, because we get a rule for this continuous random variable x, and we have to find the expected value of x. So we're going to do that by just saying, well, it's the integral sort of over the full range of x values that the function is non-zero. So in this case, that's 1 to e. Oops, and I almost fell for the trap of forgetting that x in front. Right, so we get an x here times the function, which is log e of x, with respect to x, right? So the expected value, that's what it's going to equal. Just be mindful too, like another trap that people sort of sometimes fall into is we often, when there's a number here in this position, we often say, well, we can take that out the front of the integral. When it's x, we can't do that, right? You can't take x out the front of the integral. So don't kind of fall into that trap. You just have to evaluate the integral with x inside of it. And super quickly, let's chuck that into the CAS. What do we got? Lower terminals, 1, upper terminals, let's do that, e. And then we get x. Oh, for goodness. Remote learning's been going on too long. My brain's fried. Okay. And the options were all in decimals. It said the expected value is closest to. Now, what have we got? 2.097 on the CAS. So, yep, that's matching up option E. Always a relief when you can actually see the answer that you got. Alrighty. So that's a couple of examples on how to find the mean of a continuous random variable, right? So it's just a straight application of that formula there. In this next part, we start to look at a couple of others, the median and the mode. There's a little bit here on percentiles and quartiles. I wouldn't fixate too much on this section, but it does explain what they are. But let's focus on the median and the mode. So the median, like we know from just our knowledge of statistics, the median is the value that kind of divides the distribution into half. Okay, the median we often think of as like the middle number. If it's a continuous probability distribution, then the mean is the value where, like, if you had this graph and we know that the full area under the curve is 1, well, the median's the value that you could say, well, the area below the median is 0.5 or the area above the median is 0.5. So that's a 0.5 there as well. All right, so to find the median, what you actually do is you usually go, I'll integrate from the lowest possible value up to this number m, which will represent the median. And the integral of that function, if I set that equal to 0.5, well, that's going to do the job of like finding the value of m that gives me half of the area on either side of it. Okay, and so that's what we're going to do to find the median. In a moment, I'll come back and talk about the mode after we've started this next example. So example 4a, I've got kind of a practical question here. The life in hours of a type of battery has a probability density function with the rule f of x equals, and we've got this kind of defined function over here. So the first thing that we're asked to do is calculate the median number of hours that this battery type will last. Okay, so obviously the battery is going to last somewhere between 24 hours and 30 hours because those are the defined values we have of x. If we want to know the median number, well, what we do is we say, let's say that the lower terminal is going to be the smallest possible value, theoretically negative infinity, but in this question, in practice, it's 24. It's going to integrate from 24 up until this value m, which will represent the median. We're going to integrate the function, and just to save a bit of time, I'm just going to write f of x instead of that, the entire function. With respect to x, we're going to let this integral equal 0.5, right, and solve that for m. And that should tell us the value that kind of cuts the distribution in half. And we know that just from these two values, the median has to be somewhere between 24 and 30. Okay, so we've got a bit of a common sense check for our answer there. All right, so now let's get the CAS to do a bit of legwork for us. So we set up our integral. So we're going to use m as our upper terminal. That's going to be our median. And then we're just going to put the function in. So what's it? Oops, 108. Oh, beg your pardon. 1 over 108 times x minus 24 times x minus 30 squared with respect to x, right? So there's our integral with our terminals on it. And we're going to solve and let that equal 0.5. And of course, we're solving for m, so tell the calculator to solve for m rather than x. And then hit OK. We get a couple of different values here. So we've got what have we got? 22.5 and 26.3. Remember, we said based on the domain of the function that x had to be between 24 and 30. Okay, so we're going to ignore the 22.5, and our answer will be the 26.314. It's probably a bad question because I didn't say what to round to, so let's just go to 2 decimal places and say that the median would be 26.31 hours. Right. So essentially what that's saying is that like 50% of these batteries will last longer than 26.31 hours and 50% of them will last less than 26.31 hours. Okay, find the mode of the distribution. I said we'd come back to this definition. So the mode is still, like in all ways, we sort of always think of the mode as being the most common value. So in a continuous probability distribution, the mode just occurs at the x value that has the highest probability. So it's basically just the highest point on the curve. So what we can do, coming back to our function in this question, is just find for this this graph here, and it might have been good to have graphed it before. We're just going to sketch that graph, and just so we can kind of see it nice and clearly, I'm going to set this window. So if you are over sketching a probability density function, obviously the domain of the function will give you an idea of where to set your x values. It's between 24 and 30, so I'm just going to go from sort of 22 to 32. The y values are typically really small because remember that the full area under the curve is only 1, right? So you're not going to get huge high y values. So I'm going to set my y min as, well, actually I'll make it negative 0.5. The maximum is 1. That should hopefully give us a nice sort of picture of this. Yeah, awesome. And so essentially what we're trying to find is, yeah, just the maximum value of the function between 24 and 30 in this case. And of course we can just do that by getting the maximum turning point from the graph. I don't know, I've still got the last function on the screen, so I'm going to tell the calculator I don't want that one. At least I'm going to try to. There we go. All right, and so we get our maximum occurring. Now the modal value is the x value at which that maximum y value occurs. Okay, so the mode is actually 26. So the mode of the distribution is 26 hours, and that's come from finding the x value that gives the highest probability. The other way, of course, we could have done that is using the function and using fmax. So interactive calculation fmin, fmax is just a handy one to know about if you weren't already aware of it. Fmax, so because I highlighted that expression that was already typed out, that just copies into here, which is a nice way to do it. The variable's x. We want to find the maximum between 24 and 30, so you put your domain in here, and then it'll just spit out the maximum value in that interval, and also the x value at which that maximum occurs. Okay, so if you weren't working from the graph, that would be a nice way to find the maximum value. Okay, and last part of this example, it says 90% of batteries in this distribution have a life of at least t hours. Find the value of t correct to 2 decimal places. So what we're essentially saying here is that if we, if I do a really rough sketch of the graph that we're looking at, which sort of looks something like this, and that's 24 and that's 30, there's some value t such that 90%, oh sorry, excuse me, I've gone to the wrong end there. The value of t such that 90% of the batteries last at least that long. So t would actually be somewhere down here. And what we'd be saying is that 90% of the distribution is above this value t. Right? So 90% of batteries last t hours or longer. So we're going to set it up in a very similar way to what we did the median with an unknown terminal, but this time we're trying to find an area that we're setting to 0.9. Okay, so what we can say is that the integral from t up to the maximum, which is 30, that integral will equal 0.9, and then we're going to solve that for t. Okay, so coming back, plenty going on in this case now. I'm going to actually highlight this entire sort of line that we already did when we solved for m. Now I'm going to copy that down to a new line. And just going to change the terminals. So this time we're using T as our lower terminal, and the upper terminal was 30. The function is still the same, which is why we could sort of, I just was a bit lazy and copy pasted it. And we're setting the integral to 0.9, equal to 0.9, and solving for T instead of M. Right, again, we get a couple of answers here, but we're going to pick the one that's in the domain. The domain's 24 to 30, so T has to be greater than 24, and we get 24.85. And sometimes having a quick sketch of the situation kind of helps you do a common sense check of your answer there. Like even just that very rough sketch that I drew here indicated that T, since 90% of the values are above T, T was much closer to 24 than what it was to 30. So it kind of gives us a sense that that answer of 24.85 hours is a realistic answer. So 20.85 hours. That's the end of that section.